So chapter 5 is just 3 sections, so it's another quickie. Sections 1 and 3 we're going to do first. Those are both relatively brief. And then section 2 is kind of a big beefy boy. It takes a minute to kind of get through that. So in section 1, we're going to be talking about some of these trig identities. So let's start by just describing what we mean by an identity. So an identity is just some kind of an equality statement that is valid for all values of a given variable. So for example, you could have something that's like trivial that we can call an identity. So for example, if we have like 2x plus 6, well, I know that's always equal to 2 times the quantity x plus 3. You can call that an identity. I mean, it's kind of trivial, but it's true for all values of x. Is okay with that? So what we're going to do today is we're going to build out a whole bunch of these identities that involve trigonometric relationships. So things involving sine, cosine, tangent, etc. Now, some of these are going to be things that we already kind of knew or we might have noticed already. And some of these things might be like, well, I think today they're going to be basically all things that we kind of knew already. So let's think back here. Way back to like chapter 2, when we talked about sine, cosine, tangent, we introduced cosecant, secant, cotangent. Do you remember what the relationship between those things were? So we have these 6 trig functions, right? Some of them are related. Which ones? For example, sine and cosecant. Great. How are they related? They're reciprocals. Yeah, that's the word you're looking for. Exactly. So that's going to be our first set of identities are going to be what we'll call these reciprocal identities. Just screen cap that and drop it in. Saves me some writing. And this is just taking information that I've had all the way since chapter 2, and we're just formalizing it together in one place, right? That sine and cosecant were reciprocal, so I can say something like sine theta is equal to 1 over cosecant theta, or cosecant theta is equal to 1 over sine theta. And I can say the same things about cosine and secant and tangent and cotangent. Everybody's okay with that? All right. Let's think about another relationship that we already know about. When I go to the unit circle, how do I find tangent on the unit circle? Y over x. On the unit circle, what's y? Sine. And what's x? Cosine. So we can say that tangent is sine over cosine. And if cotangent's it's reciprocal, what can we say cotangent is? Cosine over sine. So we'll go and write those things down. That'll be another pair of identities. We'll call those the quotient identities. So far, so good, everybody? So again, nothing new that we've done. We're just kind of formalizing things that we've already kind of known, and we're packaging it together kind of in a new way. And just FYI, all these identities that we're talking about here, I've already collected for you in one place on the sheet called Basic Trig Identities. So feel free to continue to write them down. It surely helps you remember things to do it, but I'm just letting you know, like, they're all in one place in the OneNote also. All right. For the next, we're going to make the following observation. So let's go back to the land of the right triangle. So let's just say we have this right triangle here. And we have SOHCAHTOA, right? So what can I say that sine theta is equal to here? It's not a trick question. It's like as stupid of an answer as you think it is. Opposite over hypotenuse, yeah. And what is cosine theta? Adjacent over hypotenuse. So let's think here for a moment what sine squared theta plus cosine squared theta would equal. What's sine squared going to be? I mean, it's just as, right? Just sine squared, right? Opposite over hypotenuse squared. Cosine. And how do I square a fraction? Square the top and square the bottom. Exactly right. I don't like using the distribute word, but that's okay because I knew what you meant. And notice here when I do that, we're going to have a common denominator of hypotenuse squared, right?
It's true.
So I'm just going to write this as a single fraction with a common denominator. Everybody okay there? Now, what does opposite squared plus adjacent squared have to equal? Hypotenuse squared. Why? It's just the Pythagorean theorem, right? Because these are sides of a right triangle. Opposite and adjacent were the legs, so that's got to be hypotenuse squared. So what's hypotenuse squared over hypotenuse? 1. So what do we have here then? Sine squared theta plus cosine squared theta is equal to 1. This is one of what we call the Pythagorean identities because the key to deriving it was using the Pythagorean theorem. Okay. What else can I get out of this? Well, let's say I want to divide both sides of this identity by sine squared. When I divide to the left-hand side, division is distributive, so I can just write sine squared under each of them. What's sine squared divided by sine squared? 1. What's cosine squared divided by sine squared? Okay, let me rephrase. So cosine squared theta divided by sine squared theta is the same thing as cosine squared theta over sine squared theta times cosine theta over sine theta. Everybody agree with that? What's cosine theta over sine theta? Cotangent. So cosine squared theta over sine squared theta would be cotangent squared theta. Everybody's okay with that? And what's 1 over sine squared theta then? Cosecant squared theta, exactly, because I can think of 1 over sine squared as 1 over sine times 1 over sine, or cosecant times cosecant, so cosecant squared theta. That's another of the Pythagorean identities. Can we create a third one? Well, probably, Mr. Kulik. You've already started writing this down again. What am I going to do to create the third one? Divide by cosine squared, right? Why not? So what's sine squared over cosine squared? Did somebody mumble it quietly? Say it loud and proud if you know it. Tangent squared. Yup. And cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. That would be our third. So we call these guys our Pythagorean identities, and I can put them all in the same place. Like that. Now to get these, this was not like anything monumental here. All I did was like drew a right triangle and used the Pythagorean theorem basically, right? I just recast the Pythagorean theorem in terms of sines and cosines. Whoop-de-doo-doo. But it's a useful one. Next observation. When using the unit circle, have you ever noticed that like sine of 30 degrees was the same thing as sine of 60 degrees? Or that sine of 60 degrees was the same thing as cosine of 30 degrees? Or sine of 45 degrees was the same thing as cosine of 45 degrees? Or sine of 0 degrees is equal to cosine of 90 degrees. Or I can say that sine of 90 degrees is equal to cosine of 0 degrees. Right? This was, what is this? 1/2. This is root 3 over 2. This is root 2 over 2, this is 0, and this is 1. Do you guys notice any relationship going on between the angles? They add to give 90. Is there a special name for that in geometry? Not supplementary. Complementary. Good. So guess what? Sine and cosine, notice they're spelt the same way except for that prefix. Do you know what that prefix stands for? Complementary. Complementary. I don't know. I can't spell. Spelling is hard. That's not, it's commentary. Thank you. At least it was a word. Just not the word we wanted, right? So, believe it or not, the same relationship exists between secant and cosecant, and between tangent and cotangent. The same complementary relationship. We're going to formalize that relationship now into a set of identities. We call these the cofunction identities. And here I've written the complementary relationship with radians instead of degrees. Right? Pi over 2 radians is the same as 90 degrees. Right? So this is just then like an angle and then its complement. Pi over 2 minus theta is just a complement to theta. Everybody agree with that? So that's all we're saying here. It's that same relationship that we might have noticed already from looking at the unit circle. Well, that's kind of neat, Mr. Kulik. And I might have noticed that as early back as chapter 2, right? When we start really developing the unit circle. Possible. All right. Next observation. So recall way back to chapter 1, we said that two functions are even if f of negative x is equal to f of x, and two functions are odd if f of negative x equals negative f of x, right? And then in chapter 3, we noticed that sine and tangent were odd functions, bless you, and cosine was an even function. Well, if that's the case, if sine is odd, what can I say then? Well, I can say sine of negative x is equal to negative sine x. Everybody's cool with that? If that's true for sine, what does it also have to be true for? Tangent, sure. And what else? Cosecant. Why does it have to be true for cosecant? It's just the reciprocal of sine, right? Is that odd relationship going to be obliterated by just making a reciprocal? No way, Jose. Right? 1 over f of negative x is just going to be negative 1 over f of x. Okay. So these all go together. We're going to call these the odd-even identities. Let's kind of just formalize this together. Bloop. So again, notice that sine, tangent, cosecant, cotangent all have the odd relationship where the negative sign gets moved out front. Cosine and secant have the even relationship where the negative sign just gets absorbed. That's it for the identities for today. We'll have another chapter of identities later. Do you need to memorize these? No. Is it going to go better if you do? Yeah. Are you probably going to end up memorizing them on the way just by doing the problems? Probably. Are the problems going to go a lot better and faster if you have them memorized? Oh, yes. If you're planning on taking AP Calculus next year, is the expectation you do have these things memorized? Yes. The equation sheet for the AP Calculus exam is a blank sheet of paper. You don't get anything. Scary, huh? Anyways, let's do some examples now of how we're going to use this stuff, right? As long as I got the thing open, let's just do some screen capping. All right. First example says find sine theta if tangent theta is equal to 3 and cosine is negative. Is this a problem we've already done? It's a chapter 2 problem. So just reminding you how we did this in chapter 2. So tangent is positive in quadrants 1 and 3. Cosine is negative in quadrants 2 and 3. So what quadrant are we in? Quadrant 3. Everybody's okay with that? So this is our theta. Now tangent theta, I remember, is y over x. And that's got to equal 3. So I can think about it as 3 over 1. But since we're in quadrant 3, that's going to tell me that the x-coordinate would be -1 and the y-coordinate would be -3. Everybody's okay there? Notice what have we just drawn here? This is a point on the terminal side of a standard position angle. Right? That's the picture I've drawn. Using that, how do I find sine? Sine would be y over r. What is r again? Yes, the hypotenuse, or the distance from that point back to the origin. So this is like, So r is going to be the square root of -1 squared plus -3 squared, or the square root of 10. And if I rationalize that, then that's -3 root 10 over 10. You guys kind of remember doing that way back in chapter 2. We can also accomplish the same thing using our identities. So let's do it that way as well. So what I'm going to do is I'm going to look for an identity that involves only sine and tangent, or only tangent and cosine. So if I go back and I look at my identities that involve tangent 1 over cotangent, that's no help. Tangent equals sine over cosine, that's close, but it has two of the things I don't know and not just one of them. That's no help. Tangent 1 plus tangent squared is equal to secant squared. Yeah, that'll do. Why is that okay? You said sine or cosine. Secant is 1 over cosine, right? Yeah, so that's the one I'm going to use because it involves tangent and then just one of the two things that I'm interested in. So it said tangent is 3. And then I know then that secant is 1 over cosine. And if I flip that to both sides, I get then that cosine is plus or minus 1 over root 10. But what does it tell me about cosine in the problem? It's negative. So cosine has to be negative 1 over square root 10. Now I can say that look for a relationship that involves tangent, sine, and cosine, since I know what cosine is. We saw that already, didn't we? That was the quotient identity. So if I multiply both sides by cosine theta, we have that. And then if we substitute we get the same thing. What was the advantage here? No geometry, no picture needed, right? This was all algebraic. That's cool. We never had to resort to that other definition of using like a point on the terminal side, that intermediary definition before we got to the unit circle definition of sine and tangent. Here, this relied on none of that. That's nice. Okay. The other type of problem that you'll end up having to do is simplifying expressions of trigonometric functions. So let's do some examples of those. Those tend to be a little bit more difficult. So this example says simplify the expression sine cubed x plus sine x times cosine squared x. So in a problem like this, we're asking you to simplify. I really have two things I can use. Okay? So I have my trig identities that we just developed. And I also have algebra. So like anything that I could do with algebra, I can do here. So I can like factor or FOIL or make common denominators or combine like terms, like normal algebraic simplification stuff. That's also allowed here. Everybody's okay with that? Now, when I'm doing one of these problems, typically the first thing I'm going to look for is an algebraic thing to do. Take a look at this expression. Do you see anything algebraic to do? Brandon? Braden? Great. So, Braden, notice there's a greatest common factor of sine x in each term. So if I factor out a sine x, sine cubed x would become sine squared x. And sine x cos squared x would become cosine squared x. Everybody's okay with the algebra step that we did there? What do you notice? Aha! No. That is an identity, right? Sine squared plus cosine squared was equal to 1. That was one of the Pythagorean identities. And I know 1 times anything is just like that thing. We're done. Can't get simpler than one thing, right? Well, that was pretty neat. This is the funnest thing we do all year. Isn't that satisfying, though, to have like that big complicated problem just turned into a little bitty thing? Let's do another example. So here we have secant x minus 1 times secant x plus 1 all over sine squared x. Again, first thing I look for is anything algebraic to do. You guys see anything algebraic here? What do you think?
Foil.
Yeah, you could FOIL that numerator out, right? That seems like a good idea. All right, real quick in your head, how do you FOIL that out?
First in the order that.
No. Just tell me the answer right now. It's a 1 second answer.
Secant x squared.
What? How did that happen so fast? That's a difference of 2 squares, right? Usually we use that as a factoring pattern. You can also use it as a FOIL pattern. Just a shortcut through that. That pattern happens a lot on these kinds of problems. It's usually a good thing to use. Okay? What do you want to use next? Braden?
Separate the secant squared minus 1, but put those two things both percent squared. So we could.
Sure, I wouldn't, but yes, you could do that. Like, there's nothing wrong with doing that. There's something that's going to make life easier to do right here than that.
Can you turn sine into cosecant?
You could do that also, Christian. You could turn the sine squared into 1 over cosecant squared. I would not do that, though, because now you're making a fraction inside of a fraction. That seems to me worse. You know what I mean?
Can you not just move it up?
I mean, you could.
So it's like 1 over sine squared.
Yeah, I mean, you can. But then again, like, okay, you're getting rid of the fraction, but now you have like 2 reciprocal things multiplied together. So when I see something squared and a 1 together, where I have secant squared x minus 1, when I see something squared, my first thought is Pythagoreans, especially if it's got a 1 added or subtracted from it. So go ahead and look at your Pythagorean identities, see if there's something good that you could do there. What's secant squared equal to? One plus tangent squared. And I love that because guess what's going to happen with those 1s up there? Yeah, those are just like terms. They'll just cancel each other out. Well, that's really pretty pleasant. So now we're down to a single fraction, right? There's not like any addition or subtraction going on. Nice. What do you want to do next? Yeah, so let's think about it this way if we're going to do that. Yeah, I would think about it, the fraction this way first, and then write tangent as sine squared over cosine squared. Which is pretty nice, because now those things will cancel out. What am I left with then? One over cosine squared. Very good. Don't forget the 1 overs. That's easy to do. And that is just secant squared. Now, Braden, you probably could have gotten to the same spot doing what you were suggesting to do. It probably wouldn't have been significantly different. But I think it's a little bit messier at this, in a place, but probably not massively. Not a terrible idea. Christian, again, what you were suggesting to do, again, would get you to the same spot, was okay to do. Just, I don't think the most obvious thing to do, but I think it would end up working if you've kept on following what you're doing. In general, for these problems, as long as you do like legal algebra and you use the identity correctly, it'll work out. It may take you 8 steps instead of 3, but it'll work out. Do you want to go through and do this same problem one of the ways that those fellas were suggesting, just for grins? Yeah. So Braden had suggested that we do this as like, that we separate the 2 fractions. Since that was 1 fraction with a common denominator, I can just separate it into 2 fractions with the same common denominator, right? I think that's what you were saying. Is that? Yeah. Okay. Is that okay to do with a numerator? If I have like 1 plus sine in the denominator, or secant squared minus. Okay, if I had sine squared over secant squared minus 1, could I do the same thing? And write it as like sine squared over secant squared minus sine squared over 1? No. You can only separate numerators like this. Okay. All right. So what would you want to do here?
I don't know, I was thinking something to do with the secant squared, because I didn't know the Pythagorean.
Yeah, this is probably where I would be thinking to go. So I would think about that as secant squared times 1 over sine squared. And I noticed that 1 over sine squared is cosecant squared. And there I see some factoring, right, Katie? Sure.
Why can't you just do cosecant minus cosecant and then it's just like 0?
No, because you have to follow the order of operations. There's multiplication going on, so you'd have to deal with that before you can do the subtraction. And notice here that we're really kind of like back to the same thing we had here, right? We're just written not as a fraction, which was going to end up at the same spot that Christian was suggesting by writing sine as 1 over cosecant and then multiplying it to the numerator, right? So what you're still left with is you have to do secant squared is 1 plus tangent squared. And then you're just at the same stuff that we were doing. So eventually you had to use that identity somewhere to kind of get any further, it seems like. Is everybody okay with like me hand waving it from here? That it's now just the same problem that we had, or got to basically the same spot we were before. Just took a few more steps to get there. I can't think of another more clever way to kind of sidestep having to use that identity. I don't know that there would have been one short of, yeah. Well, I guess I could think of one, but it just ends up using a different Pythagorean. But not very exciting. Let's do another. Okay. How about here? Simplify the expression cosine over 1 minus sine x over cos x.
Sine x over cosine x, can you make that 10?
You could. I probably wouldn't in this point because I usually look for algebra stuff before I start diving into identities. But it's not wrong. I want to be clear. Not wrong. What kind of algebraic thing could we do here? Make a common denominator so we can subtract these two fractions. That's what I would do first. Again, Christian, what you were suggesting, not wrong by any means, but at some point you're going to need to make a common denominator, and it's probably going to be easier before you start monkeying around with the trig identities. So that common denominator is just going to be cosine x times 1 minus sine x. So my numerator, I'm going to have cosine squared. And I have minus sine x plus sine squared x. Everybody's okay with why it's plus sine squared? Because the negative has to distribute also, right? Okay, we've made our single fraction. What do you notice?
That there's cosine squared and sine squared.
Yep. Great. So those, I can add those together even though they're not right next to each other, right? Because the associative property still holds. These are just numbers we're talking about. They're not being multiplied to anything else. Woo! What now? Yeah, we can reduce. Oh, just as an aside here before I go and start doing any more. Notice back at this step, I multiplied the numerator out, but I didn't multiply the denominator out. Why did I just do it like halfway like that? Why wouldn't I have multiplied the denominator? How did I know, other than I've done this problem a bunch of times in my life? How, in general, though, I would have known that even if I hadn't done this problem before. Here's the reason. Okay, here's the reason. If I want to reduce a fraction, it's got to be in factored form. The numerator is going to be subtracted regardless, so I have to distribute the numerator out and combine like terms before I could factor. The denominator, though, is just two things multiplied together. That's already going to be factored. I'm just going to leave that be, because if there's any reducing to do later on, I want it in the factored form so I can do the reducing, right? Whenever you make a common denominator and add fractions, don't multiply out the denominators. It's just a waste of your time. Just leave it in the factored form and worry about the numerator, and then factor that after you've combined like terms to see if you can reduce. Which we can here, correct? So what am I left with? 1 over cosine x, which is secant. How we doing here, folks? All right, next example, simplify the expression sine x times cosecant negative x. Anything algebraic? No, man, you just have two things multiplied together. Unless they're like terms, there's not going to be anything I can do algebraically, right? Okay? So it's identity time. What identity would I want to use first? The first order of business is my variables are different. One of them's x and the other's negative x. I need to get those to be the same variable because I won't be able to combine any like terms at any point until those are the same variable. So I'm going to use the odd-even identity for cosecant. Exactly right. Everybody's good with that? Now, what do you want to do? Use the reciprocal identities. Great. Which one do you want to do? Turn cosecant into 1 over sine. What were we left with? -1. Woo! Isn't that cool? I love when that kind of thing happens. All right, one more example, and we'll call this a day. All right, simplify the expression cosine of pi over 2 minus y times cotangent y plus tangent y. Anything algebraic to do here? Doesn't look like it to me. So maybe we look for identities then? What identity would we want to use first? I would say there's a right answer to this. Yeah, we'd want to use one of the cofunction identities because, again, we see that the variables are different. One of them is pi over 2 minus y, and the others are y. So I would use the cofunction identity. Cosine of pi over 2 minus y is just going to turn into sine y.
I'll go past this one.
Everybody's okay with that? What would you like to do next? Okay, either one is fine. Anybody have a preference? You like rewriting those two first? I like that too. Worth stating that there'd be nothing wrong with writing cotangent as 1 over tangent. That would have been okay also. Because the next step would be the same regardless of what you did, whether you want to write cotangent as cosine over sine and tangent as sine over cosine, or want to just write as 1 over tangent plus tangent, or cotangent plus 1 over cotangent. Any of those is fine. Because I would say the next step should be I would make a common denominator here to add these two fractions. So I'm not going to do any distributing yet. You could, not wrong to do that, but I think it's going to actually be neater if I wait on that. What would the common denominator be for those cosine over sine plus sine over cosine? Yeah, sine times cosine, right? So the first fraction I have to multiply by cosine over cosine, correct? So that gives me a cosine squared. The second fraction, what do I have to multiply by? sine over sine. So that'll give me a sine squared in the numerator. And the numerator there is 1. That's really nice. And what do we see? We're left with 1 over cosine, which is just secant. Boom, goes the dynamite. All right, what am I going to ask you guys to do is 1 through 14. And I think worksheet 2. For the asynchronous day, I have a video for 5.3. It's only like 10 minutes or something, so it's not like a big time investment. And then you're going to work on problems 47 through 62. .3 is basically the same thing we did today, except it's like a proof, which makes it easier because you're given the correct answer. Your job is just filling in the steps to get to the correct answer. It's the exact same process that we did today, except you know the end already at the beginning, and it's just a question of like filling in the steps to get there. Okay, with that idea? So using the same techniques, algebra, and our identities, and you're told what the answer needs to be, you just got to do the steps correctly to get there. Okay, I think in the video I have, I don't know, a couple, 3, 4 examples and some kind of general guidelines to help you. But that's the gist of it. Everybody's okay? Feels okay? Feels all right? Yeah? Yeah? It's like I just got to get into it and do some practice. All right. I'm going to stop here.